Hi everyone. Today we're going to be talking about Unit 5 and Unit 6 in this lecture. And Unit 5 is going to cover ratios and proportions. So a ratio is a way to show a relationship between two items. We're always counting and comparing items in our daily lives. You probably don't even think about it. Work hours, for example, versus hours away from work, or the number of candy bars we've eaten versus the number of candy bars that are still to be eaten in the bag, and so on and so on. So ratios simply help us compare items, objects, or amounts. Now, proportions compares two equal ratios in a mathematical equation. So we use proportions to either increase or decrease one part of the ratio in the equation so that the unit expressed or found is in the same relationship with the other part of a specific ratio. And so that this ratio, when completed, shows the same relationship as the other ratio. Well, this is all going to make sense, so hang in there. So a ratio is used to show a relationship between two numbers or a comparison of two items. The numbers are separated by a colon, like you see here, as in 3 to 4. 3 nurses to 4 medical students or medical assistants, for an example. We can also write this in several formats. So the first one, when we are comparing the ratio of nurses to medical assistants, we can write it 3 with a colon and then a 4, or we can write it as a fraction, 3 over 4, or we can also write 3 is to 4. 3 nurses to 4 medical assistants. So writing your ratios in the proper order is really important. Follow the order of each number of the ratio in the sentence or the problem. So it's a good idea to include the units. This is going to help you stay honest, right? Help you reduce errors when you're working with ratios or proportions. So this way we can be sure that we followed the same pattern in each ratio. A relationship can represent something as simple as the 1 to 3 ratio commonly used to mix frozen juices, right? 1 can of frozen juice concentrate to 3 cans of water. That would be a ratio of 1 to 3. I use the same thing. I like hummingbirds, and so I make hummingbird food, and the ratio is 2 to 1. 2 cups of water to 1 cup of sugar. So that would be a 2 to 1 ratio. Ratios are, in essence, fractions that represent a part to whole relationship. Often when we work with ratios, we use the fraction format, and this just helps us to reduce the ratio to its simplest form. Now, ratios are always reduced to their lowest forms, just like we do with fractions. So, for example, if we get 8 hours of sleep in a 24-hour day, we can write that as a ratio of 8 to 24, or 8 over 24. Now, let's look at this example. Can we reduce this? Well, yes, we definitely can, right? If we factor that out, we have 8 times 1 to get 8, and 8 times 3 to get 24, and we can cancel those 8s out, and that gives us 1/3, right? So the ratio would be 1/3. All right, so let's talk a little bit about simplifying. Remember, we've simplified before, and when we're simplifying a ratio and we have something like 4.5 to 6, then we need to be able to simplify this. So remember how we get a mixed number into a fraction? We have to multiply the 2 times the 4 and add the 1, right? And this gives us 9 halves. So the first step is to turn that mixed number into a fraction. So when we do that, we get 9 halves divided by 6, and 6 is really 6 over 1, right? So now we have 9 over 2 divided by 6 over 1, and now we need to multiply those, or to divide them, and the way we do that is we reciprocal the fraction to the right of the division sign, and that gives us 1 over 6. So then we can just multiply straight across, and we get 9 over 12. And when we reduce that down, we get 3/4. All right, so our ratio is a 3 to 4 ratio when that is reduced down. Drug labels are another place that ratios might be seen, right, in the operating room or in the healthcare setting in general. So careful reading of the drug label is going to help us locate the dosage of the medication per tablet, or let's say per amount of solution. Notice that each label uses a specific language to indicate a ratio. So there are some formats listed here for you. The first one is milligrams slash milliliters, right? So this is so many milligrams of medication per so many mLs of solution, solute to solution. Remember back to our chemistry chapter in anatomy and physiology. The next one, common one, is micrograms to milligrams. The next one is milligrams per tablet. So you might see a ratio this way as well. And then lastly, milligrams in milliliters. So many milligrams in so many milliliters. All right, and these are ratios that you are going to see on drug labels. So careful reading will help you to identify which is in each tablet or each milliliter of medication. So check out this drug label. This drug label is for lorazepam, and it says here that each milliliter contains 4 milligrams of lorazepam. So we can write that ratio as 4 milligrams per 1 ml. Now, if it's just 1 milligram or 1 ml or 1 whatever, they typically do not write the 1. So if it's written this way that you see it here, 4 milligrams slash ml, that means per 1 milliliter, okay? Another example of ratios in healthcare comes from dealing with insurance coverage. So there's something called the medical loss ratio. This is used in managed care to measure medical costs as a percentage of premium revenues or income. It's a type of loss ratio used to measure the percentage in premiums paid out of claims rather than expenses. A desirable ratio is 17 to 20 or 85% or less. So another example of how this can be used in the healthcare arena. In addition, ratios can compare two items. All right, two items. For example, ratios are often used to find the unit rate, which is a rate having 1 as its denominator. Rate is a ratio of two measurements having different units. The unit rate is a rate which has 1 unit as its denominator. For example, $4.10 is the price of a package of gauze strips, let's say, and 24 is the number of strips in the package. Okay, so we pay $4.10 for an entire package of gauze strips, and there's 24 gauze strips in that package, right? So we can write the ratio as you see it here. So how do we get the unit rate? We want to know, well, we know it costs $4.10 to buy an entire package, but how much does it cost to buy one? Right? So what we would do here is simply divide 24 up into $4.10, and that gives us 0.17 some odd numbers, right? Or approximately 17 cents per sheet. So we could write this ratio as 17 cents to one sheet, or 17 to 1. Proportions can be applied to almost every healthcare profession in one way or another. In addition to on-the-job applications, proportions also provide a simple and quick method for solving many everyday math problems, such as measurement conversions, recipe conversions for increasing or increasing the amount of ingredients, and map mileage. Proportions are two or more equivalent ratios or fractions in which the term of the first ratio or fraction have the same part-to-whole relationship as the second ratio or fraction. So we set them equal or equivalent, right, on both sides of the equal sign. So let's look at an example. If we have one box of gloves, all right, and there's 100 gloves per box, then how many gloves are in 4.5 boxes? All right, so this is how we set this up. Now, here's a little tip. Notice how the terms for each category are across from each other. And this is where it really comes in handy for you to write out the units, the terms, the items, whatever it is, so that you can set this up appropriately. Because if it isn't set up in this way, then you're going to get an incorrect answer. So boxes in this example need to be across from boxes on the other side of the equal sign, and gloves need to be across from gloves, right? So labeling, really important when we are setting up a proportion. All right, so then the way that we would solve this is we would go ahead and cross multiply. That would give us x, right? Because we're going to multiply one box times x, 1 times x, that gives us 1x, or just x. And then that's going to equal 100 times 4.5 boxes, all right? And that's going to give us our number of gloves. So intuitively, you might say, well, 100 times 4.5, that's what we need to do, right? Intuitively. But this is how we would set up the equation. So to test the two ratios or fractions to see whether they're equivalent, we multiply diagonally, or what we say cross multiply, right? If the two numbers that are diagonal result in the same number when they are multiplied, then you are working with a proportion. Proportions are powerful tools in healthcare, and you can rely on them for solving a majority of your math conversions and problems. So let's take a look at this, right? This example, 4 times 15 equals 60, right? We're cross multiplying here. We have 3/4 equals 15/20. Is this true? Or is this false? Well, we cross multiply to find out. And when we multiply 4 and 15, we get 60. And when we multiply 3 and 20, we get 60, right? So this is a proportion. So the ratio and proportion method is used to solve for x, right? We're going to solve for an unknown. X is what we don't know. Solving for x uses the known or given information to find out what is not known or what isn't given. So since a proportion consists of two equal ratios, the relationship between the numerator and the denominator of each fraction is the same for each ratio of the proportion. So this is important to know when we must increase or decrease a solution or mixture, because the ratio of ingredients needs to remain constant. Let's say that your recipe says you need 2 cups of flour to make a batch of cookies, but you want to make 2 batches, right? So you would double that and you would use 4 cups of flour. This is essentially the same thing. So we're going to set the problem up like a fraction. And if there are units, we want to make sure we use those so that we set this up correctly. Then we're going to cross multiply and set the ratios up like fractions using a vertical line. So the second step is going to be to divide the answer from step 1 by the remaining number. So here we have 3/4 equals what? Over 16, right? So we want to make an equal proportion on the right side, but we don't know 3/4 equals what 16ths. Okay, so the first thing we're going to do is cross multiply. And we're going to multiply 3 and 16. You can see it circled there. That gives us 48, right? And then we're going to go ahead and divide the answer from step 1 by the remaining number, which is 4. All right. For me, when I work this out, I typically set it up as 48 equals 4x, and then I divide by 4 on both sides to get x by itself. So either way that works for you, you still get to the same answer, right? So here's some approximate equivalents, and this is a good chart for us to have handy when we are working with proportions or we're doing conversions. This table can actually be found on page 139 in your textbook. So let's look at an example. This one says, sometimes dental assistants need to mix dental stone material for dental molds. So the amount of stone and water varies according to the size of the mold that they're going to use. A dental assistant learns the importance of mixing a uniform and consistent material for the mold, right? This is important for success. So this task uses a metric system. Dental stone is measured by weight in grams, and room temperature water is measured by volume in milliliters. So the typical ratio is 263 grams of dental stone powder to 80 milliliters of room temperature water. So dental assistants use this ratio as the standard to solve variances in either stone or water to create the proportionate amount of material for the mold. On occasion, they might also be asked to use other ratios of dental stone to water depending on the type of material or mold being created. All right, so we're going to use this ratio and we're going to look at an example. Okay, so here we have our example. And the example is the dentist is requesting a smaller mold using 35 mLs of water. So how much stone should we use? Now I think it's easier so I'm going to try to use my pen to write this out. And remember before we said we have a ratio of 263, sorry, this is bad writing with my pen, grams, right, of the stone. And then we have 80 milliliters of water. Okay, that's our ratio that we use. Now, when we set this up as a proportion, we want to find out how much powder, right? So that's going to be our x, okay? And we know how much water, right? This is 35 mLs of water. That is a very bad 35 mLs. Okay, so now you can see how we can cross multiply here. So in the step 1, we're gonna multiply 263 times 35, and that's gonna give us 9,205. All right, and then we're gonna multiply the 80 and the x, and that's gonna give us 80x. Right? So really what we have is 9,205 divided by our 80, right? Because we have to get x by itself. And so we would divide both sides by 80. And that gives us 115.0625 what? Grams of stone that we need to use, right? And this is telling us to round to the wholes number. So we look at the 5 here, and then we're going to look at the number to the right, and it is less than 5, so we would leave it at 115. So our proportion would be 263 grams per 80 mLs is equal to approximately 115 grams to 35 mLs. And if you would write that in for x and cross multiply, then you should get equal numbers on both sides of the equal sign. Okay, so let's look at an example of a word problem dealing with proportions. When solving word problems involving proportions, we want to set the problem up so that the same types of elements are directly across from one another. Then we're going to multiply diagonally, cross multiply, and then divide by the number that is left to find our unknown. All right, so make sure you understand the story problem and then place the known information on the left side of the proportion, and make sure you use your units or your labels, and then set up the unknown information on the right side of the equal sign. So by doing this, you won't switch the ratio relationships, but instead rely on the known part to whole relationships, and that should help you solve the problem. So let's look at our example. If 12 eggs cost $1.49, how much do 18 eggs cost? All right, so let's set up the problem. Eggs over cost equals eggs over cost. Okay, so on the left side, we're going to plug in what we know. We know that 12 eggs cost $1.49. So we set that up that way. Then we place the equals, and then on the right side of the equal sign, we're going to place our unknown. We know that we have 18 eggs, and so we're going to place those next to the 12 eggs, right? So that they're on the they're across from each other. And then our unknown is the cost, so it goes under that. That's our x. So all we have to do is cross multiply the two numbers, which is $1.49 and 18 eggs, and we get $26.82. All right, and then our second step is going to be to divide by the number that is left, and that is 12. And when we do that, we get $2.24 when we do our rounding. Okay. So let's look at a more complex problem with decimal numbers. So decimals and fractions may appear in your proportion problems. Although the numbers may be visually distracting, the very same principles are going to apply when we're solving these problems. So let's look at an example. So here we have 0.25 milligrams per 0.8 milliliters equals 0.125 milligrams per X amount of milliliters. Okay, so we're just going to set this up the same. Remember, if it helps you to just initially do a separate fraction with milligrams over milliliters equals milligrams over milliliters. Then plug in what you know on the left side of the equation and then plug in what you don't know on the right side. So that's what they've done here. So we put 0.25 milligrams over 0.8 milliliters, that's what we know. So this is saying that we have a medication that contains 0.25 milligrams of solute of the good stuff, right, to some sort of solution, 0.8 mLs of solution, fluid stuff, okay? And so now they're asking us, okay, if we have 0.125 milligrams, how many milliliters is that? All right, so the way that we're going to set this up is we're going to cross multiply our two numbers, 0.8 and 0.25, and that gives us 0.1, and then we divide by the number that is left to give us our x. Right, so we divide by 0.25, and that gives us 0.4 mLs. Remember, we can check this by plugging it back into our proportion for x and cross multiplying and see if we get equal numbers on both sides of the equal sign. So carbohydrates, fats, and proteins provide fuel for our bodies. We already know that. Well, these factors are easily applied by using proportions to solve for an unknown. So here we have another example, but this time we're talking about calories. So in the example, we have 400 carbohydrate calories equal how many grams? All right, so let's look at what our chart tells us. So we're going to set this up grams to calories and grams to calories. Okay, so once you set that up, then you can plug in on the left side the information that you know. What do we know about carbohydrates? We know that 1 gram of carbohydrates equals 4 calories, right? So we can set up the stuff we know on the left. And then the problem is asking us how many grams is 400 calories. So the x is the grams, what we don't know, and the known is 400 calories. So now we're going to cross multiply 1 gram and 400 calories, and that gives us 400. And then let's divide by the number that we have left, which is 4, and that gives us 100. So it's easy to see if we were to plug in, if we were to plug in 100 over here, I cannot draw appropriately with this, and cross multiplied 4 calories by 100, we get 400, and 1 gram and 400 calories, we get 400, right? So we'd have 400 on both sides of the equal sign, and that would let us know that we got to the right answer. So knowing how to read food labels is also important because patients often need to limit their salt or their sugar or their fat intake to help ensure good health, and we can use that in our personal lives as well, right? So proportions are useful in figuring out the amounts of these ingredients when portioning, whether we're increasing or decreasing our portions. So carefully read the label and then we're going to look at an example on the next slide. So here's our food label. It's some tomato soup that we're looking at. So again, knowing how to read these labels is important, both professionally and personally, and it's not out of the scope of the surgical technologist's practice. Let's say that you're working in labor and delivery. It is not uncommon for the surg tech to also serve as a unit secretary, as well as placing food orders, meal orders for the patient, delivering food orders to the patient, those kinds of things. And so this can definitely be used in our professional lives as surg techs as well. And so here, let's just take a quick look at this. We're not going to do too much with this, but here it says the serving size is about half a cup, and then it gives us that in milliliters, 120. It also tells us the serving size and then how many calories per serving size. And then let's look at the other portion here. We have, it gives us the total fat, which is 0 grams, 0 saturated fats, 0 cholesterol. It contains 710 milligrams of sodium. And then it also gives us our percentages of vitamin A, C, calcium, and iron. And then it gives a total number of carbohydrates. All right, so if we wanted to figure out how many carbohydrates would be in 2 servings or 2.5 servings, or how much sugar would be in half a serving, those kinds of things, we could definitely set this up as a proportion. All right, so now we are going to talk about Unit 6, which covers measurement conversions. So as healthcare workers, we rely on a variety of math systems to achieve our daily tasks. So knowing different ways to convert efficiently among math systems are going to benefit us on the job as our expertise grows and our level of responsibility increases. So it's important to have the ability to convert among math systems and measurement systems. Previous units reviewed each of these math skills separately, and so now we're going to put them all together. Okay, we learned the dance steps. Now we're going to do the dance. In Unit 4, we learned the metric system, and we studied ratios and proportions in Unit 5. So these are essential in converting among measurement systems. So in this unit, we're going to use those 2 math skills to convert among the systems of measure. So this unit's going to cover metric, household, and some basic apothecary conversions. Apothecary conversions are specifically addressed again in Unit 11. So here we see some examples of different types of measuring tools that we might use in the healthcare setting. Medicine cups and syringes are 2 that we will use on a daily basis as surgical techs. Also, graduates' bowls and basins will also use and need to measure either amounts of fluid used or amounts of fluid left, those kinds of things. And so this is really a useful skill for us as surg techs. So learning these skills will enable us to move between measurement systems easily to make sure that we're giving the correct medication to our patients. So again, important tool for us, whether it's using it daily in our personal lives or in our professional lives. But this unit is going to cover 3 specific measurement systems, and those are household or standard measurements like cup, teaspoon, tablespoon, quart, gallon, pint, those kinds of things. Also the metric system and apothecary measurement. So household and standard measurements are pretty much the ones that are used in our daily lives, and sometimes they're used in the healthcare setting as well. In the operating room, we might not come into contact with those as much. I do know that medicine cups will have mLs and ounces, and ounces are something we do use in daily activities. But we usually report the mLs and not the ounces in the operating room. So again, in the healthcare setting, they might be used for less critical measurements, like maybe you're mixing some mop water and it's so much of your solution to water or something of that sort. They do tend to be less accurate than the metric or apothecary measures. So looking at this table, we can see the units of measurement used to measure height, weight, liquid volume, and medication dosages. So for height, there are units of measure like feet and inches, which we should be really familiar with, and also meters and centimeters. For measuring weight, pounds and ounces are probably more familiar to us, but we also use kilograms and grams, particularly in the healthcare setting. Liquid volume can be measured using gallons, quarts, pints, cups, tablespoons, and teaspoons. There's also liters, right? And then medication dosages, we can measure those by the tablespoon, the teaspoon, a tablet, an ounce, a capsule, a caplet, and also milliliters, milligrams, micrograms, those kinds of things. All right, so let's look at abbreviations. If we are going to abbreviate, instead of writing out a word, it is really important that we abbreviate it correctly. And as surgical technologists, not only is it important that we are able to read and decipher our own writing that we're going to be placing on medication labels, but that our team can read it and decipher it as well. And in addition to that, as a surg tech, you will be relieved during a case, whether it's for a lunch break or maybe you're in a long case and you're being relieved so you can go home at the end of your shift. Either way, that person that relieves you needs to be able to read that label. That is a very important communication tool, and we want to make sure that when we are writing our medication labels that we're writing them correctly and we're writing them very clearly. And so that's something that we'll be looking for as instructors as we move forward in the lab. So some abbreviations here for units of measure that you see, and there are many, many of them. Just a couple examples where we abbreviate a drop as GTT, a teaspoon as T or TSP, a tablespoon is a capital T or TBSP, and cup as a C. Now, we probably won't be using these too much in the operating room. What we use most is milliliters and potentially milligrams. So the basics of standard measure conversion were covered in Unit 5, and we had a nice chart that they gave us in Unit 5. So to refresh ourselves on the application of proportion to measurement conversions, we're going to look at some exercises, and practice is what is going to help us become proficient at this. So don't be afraid to dig into your textbook and do some of the practice problems that are in there. So here we see if we're focusing on conversions, an example might be converting tablespoons to milliliters. All right, and so you know, a tablespoon equals 15 milliliters. And we'll see that on the next slide. But some examples here, maybe we need to convert pounds to kilograms. And so this chart tells us that 1 kilogram equals 2.2 pounds. So we would be able to use that information and set up a proportion to solve for our unknown. And again, here are some additional conversions. We're looking at tablespoons, teaspoons, cups, pints, quarts, and gallons. We would be able to use this information to perform our conversions. So the apothecary system. It's an old and antiquated system that is used for measuring medication, and honestly, we probably won't use this too much in our professional lives. However, it is very important that we have an understanding of these concepts because we are the extra eyes and ears for our patient. And whatever is going on in that operating room, we need to have at least a basic foundational understanding of it, right? Because we are held responsible for our patient's care and safety. So, having said that, back to the apothecary system. It's an older system that's used for measuring medications, and more than likely, medication labels will also include metric and household units in addition to the apothecary units. Some units in the apothecary system include ounces, drams, and something called grains. Now, grains were traditionally used to measure certain medications like morphine and aspirin. The apothecary system used fractions, Roman numerals, and whole numbers to indicate measures. So today, in the healthcare industry, uses primary whole numbers and decimal numbers to indicate amounts. Household and apothecary systems use the same units of measure. So in other words, a household ounce is equal to an apothecary fluid ounce. So in Unit 11, again, we will revisit apothecary units. So these units from the apothecary system express medical units. And so again, in Unit 11, we'll look at this more. These units are slowly but surely being replaced by the metric system so that medication dosages are more uniform. This is a serious situation. I know that electronic medical records, some of them convert from pounds to kilograms, some of them do not, some of them use pounds, some of them use kilograms, and this is seen in several places in the healthcare system. There isn't a standardization across the board, and so we have to be really cognizant of that. If you are in a position as a surge tech where you're working more with electronic medical records, as I mentioned, maybe in labor and delivery or some other non-traditional role that the surge tech may be in, that you have a heightened awareness of the medical record system that you're using and these conversions, especially with peds. Pediatric misdosages or miscalculations of medications are the number one reason that pediatric patients die in the hospital. So this is something that is very important for us to keep in the forefront of our minds. All right, so here this chart is just giving us additional information about different units and their equivalents. All right, so here we go. We're going to look at our first measurement conversion. And in this example, we are converting kilograms to pounds. So again, set up our equation, kilograms to pounds equals kilograms to pounds. Now, you can set this up as pounds over kilograms equals pounds over kilograms. It doesn't matter. What does matter is that your units are across from each other on each side of your equal sign. So here, let's look at the left side first and determine what we know. And what we know, if we look at our handy dandy charts that are provided in our text, and they start on page 159, it looks like. So you can use that to find your knowns. And so if we look at that on page 159, under weight, it says 1 kilogram equals 2.2 pounds. So we can plug in what we know, and we've done that here. 1 kilogram per 2.2 pounds. Okay, so let's look at the other side. What do we know and what don't we know? Well, we know we want to convert kilograms to pounds, and so we're looking at 45 kilograms. So we're going to set that across from our other kilograms. We'll place 45 kilograms on the top as the numerator, and then underneath that is going to be our x, right? That's going to be our unknown. So let's look at how we work this out. Okay, so remember the first step is that we need to cross multiply the two numbers that we know, and that's our 2.2 and 45. So when we multiply that together, we get 99, and then we would divide by the number that is left to find our unknown. And the number that is left is 1. And so when we divide 1 into 99, we get 99. And so our answer would be 99 pounds. Now, intuitively, you may be able to look at these simple conversion problems and say to yourself, oh, well, if we have 45 kilograms, then I know that I just need to multiply that by the pounds. Or if I have so many pounds, I just need to divide that. All right, so you might be able to intuitively look at this and get to your answer, but I would highly suggest writing this out just to make sure that you don't make a mistake. All right, so as far as formatting goes, the format of your final answer may vary by the measurement system that you're using. Metric units typically use whole numbers and decimal numbers. For example, we might have 4 liters, or we might have 12.3 kilograms, or 0.25 milliliters. Now, household and apothecary units typically use whole numbers and fractions, like a half a cup, a quarter of a cup, 3.5 pounds, those kinds of things. All right. And then lastly, drops, if we're talking about drops. Drops are always whole numbers, like 5 or 3 or 2 or 150. Okay. So a helpful hint, when using a fraction in the household system, it's easy to put that fractional part in a decimal format so that you can use it to work with metric units, right? For example, if we have half a teaspoon, then we know that is 0.5. Or if we have a quarter of a teaspoon, that would be 0.25. Okay, and then we can easily do our conversion to find out how many milliliters would be in half a teaspoon or something of that sort. Now be sure to use the conversion factor that's closest to the units that you're working with, because the conversion factors are ready for the most common conversions. Sometimes measurement conversions require more than one conversion to get to the answer. These problems can't be solved by just making a straight conversion from what is known to what is unknown in the proportions that we've been setting up. So far, we've been performing straight conversions, all right? So if we're unable to perform a straight conversion, then a path has to be developed so that we can establish how to get to the answer. So I want to think about what conversions most closely match the problem itself, and then that's going to help us set up the problem. So let's look at an example. Okay, so let's look at this example. Here, we're wanting to convert ounces to teaspoons. So in order to convert ounces to teaspoons, we have to first convert the ounces to milliliters. So what we know is that there are 30 milliliters to 1 ounce. All right, so if we have 8 ounces and we want to know how many teaspoons is equivalent to 8 ounces. So first we have to convert our ounces to milliliters. And then we can convert our milliliters to teaspoons. So we're going to set this up in the same way, right? We know that there are 30 milliliters in 1 ounce. And so 1 ounce per 30 milliliters, and then we're going to put our equals, and on the other side it's telling us we have 8 ounces, right? And we want to know how many milliliters. So then we can perform our operations where we cross multiply 30 and 8, and then we would divide by 1, and that gives us 240 milliliters. Now we know what we need to know to find out teaspoons. So let's look at that on the next slide. All right, so our chart on page 159 tells us that there are 5 milliliters in 1 teaspoon. Okay, so we're going to set up teaspoons to milliliters. So we have 1 teaspoon is 5 milliliters, and we set that up on the left. That's what we know. And on the other side, we're going to set up making sure that our units are across from each other, X number of teaspoons over our 240 milliliters. So then we're just going to cross multiply our 1 and our 240, and that gives us 240. And when we divide by 5, we get 48. And 48 is our teaspoons. And if we were to plug 48 back into for our X and cross multiply both sides, we should get 240 on both sides of our equal sign. And that's how we would do a multi-step conversion. So lastly here, plastic medicine cups, like I said, are often used. We'll see these as surge techs day in and day out, to measure liquid dosages like different local anesthetics and contrast dye that we use in the operating room during surgery. So one of the most common ones is a 1 fluid ounce, which is 30 mLs. And sometimes we have 2 ounce ones too that are 60 mLs. And so this might be typically in the operating room, we're not going to be doing conversions on the fly. Our medicine cups will usually have milliliters and ounces or cc's on there. So don't get too worried about that. However, if there is something like this, the situation that comes up, we are prepared and we have an understanding of how to do these conversions so that we can perform those accurately. Thank you so much for listening to this lecture and taking the time to understand conversions and working with different units of measure.